Hello everyone. Welcome to Zero to Gradients YouTube channel. This is the very first video of our series Mathematics for Machine Learning. For learners, it might be intimidating to jump directly to gradient descent or let's say linear algebra or any statistical models. But personally, I felt that learners should be aware of functions without any ambiguities regarding them. I will not go too abstract, ensuring there is some good balance of intuition and formal definitions. So yes, what is a function? Let's start the story by considering two separate sets. Now, what are sets? Sets can be defined as well-defined collection of distinct objects. Well-defined meaning we can clearly decide whether something belongs to the set or not. And each element is unique. I mean, no repetitions, okay? So we call these objects as elements of a set. Let's consider two such sets, set A and B. In set A, let's consider Mike, Will, Dustin, Lucas, Jonathan, and Steve. And in set B, we have Max, 11, Nancy, Robin, and Major General Dr. K. Now imagine that people in set A and set B are strangers to each other. We now want to describe possible relationships between these people present in set A and the people in set B. To do that, we consider all possible pairings between elements of set A and B. This is called the Cartesian product of A and B. Each pairing is written as an ordered pair A, B, where order matters. The first element comes from set A and the second element from set B. Such objects are also called as tuples. This Cartesian product or cross product of A and B is also a set. More specifically, set of all possible ordered pairs which are in the form of tuple. In our example, it looks like this. Notice that the order of the pairs are maintained and all possible pairings have been formed. Some might mistakenly call it grouping instead of pairing, but this can be confusing at times because grouping means unordered collections or subsets. So it's imprecise to call the pairs as groups. And one more important thing, this is neither permutation nor combination. Note this importantly because we are not arranging or selecting the elements, rather, we are forming ordered pairs. Now note that I said that A cross B, I mean the Cartesian or cross product between the set A and B is also a set. Now that we have all possible pairs, we do a filtering step. Here, we do the selection from these possible pairs, I mean within the cross product. So yeah, the result of this selection is what we call a relation between set A and B. Note that we can select all possible pairs from the cross product or select none, meaning that the result of no selection or the null set is also called a relation between set A and B. So let's have a quick recap. We started from two separate sets, right? And how exactly did we arrive at the stage of having a relation between those two sets? We will clear one possible misunderstanding here. Step 1, we take the cross product. And here you have to remember that just taking the cross product doesn't mean that the relation is established. And in step 2, we perform selection within this cross product set. This includes the case of selecting all elements or none, or I mean null set. And this result of selection of ordered pair is what we call a relation. Okay, so now that we understand what a relation means, let's now get to the core concept of functions. Here first, let's observe the cross product set. In this ordered pairs, we shall make a selection like this for example. Okay. So now that there is a subset of the cross product set, this is obviously a relation. A function is also a special type of relation but with certain conditions. And those conditions are as follows. Every element from set A should be present inside this relation, and every element from set A should be orderly paired with exactly one element from set B. I mean, order is very much crucial here. And no element from set A should be left out, and it should not be paired with more than one element from set B. In this example, we can see that all elements from set A are paired with elements in set B. Will cannot be left out here because he is in set A, but there is no condition that every element from set B should be included. Set B elements can be left out. Dr. K is left out and that's acceptable, means that's totally fine. And according to second condition, no element from set A should be paired with more or less than one element from set B, meaning might should be paired to 11 or max or any one person. That's it. But never more than one pairing or even no pairing. That's also not acceptable. But yeah, multiple elements from set A can be paired to a single element in set B, meaning both Steve and Jonathan can be paired with Nance. In set theory, we call this left total and right unique. So yes, basically function is a rule which maps all the elements of set A to exactly one element of set B. We call set A as domain and set B as codomain. And what is the rule here? Here the rule is individually stated for all elements in set A. I mean explicitly stated. So if we define this function with the name, it will look something like this. And one more important thing. If the same rule is present for different sets, I mean if I add an element to set B, it's not the same set as before. So let's call it set B2. But the rule is same. That doesn't mean that the function is same as though. Because function is not unique based on just the rule. Its identity is with respect to the rule, domain and codomain. All three comprised together. So if you even change the codomain, even if the rule is same, it's no more the same function. Elements of set A are called inputs and whatever value from the codomain will be mapped for them through the function will be called as outputs. So in this function, all the boys are inputs for the function and respective mappings are output for specific inputs. Now let's look at another example. This is how you are supposed to read it by the way. F from R to R defined as f of x is equals to x square. By the way, R means set of real numbers. So the rule will usually be in the form of an equation. Here it is f of x is equals to x square. Set A or precisely domain in this case is set of all real numbers and same is with the codomain. We can see that the rule maps every element in the domain to exactly one element in codomain. Now let's understand three properties of functions. So the first one being injectivity. If every element from domain is being mapped to an unique element in codomain, then that function is injective. In our example, it's not injective. In simple words, injectivity is defined in a way such that different inputs should map to different outputs. Let's take a simple case here. The function maps both -2 and 2 from the domain to the same output in codomain, meaning f of -2 and f of 2 both equal to 4. Now our function fails injectivity. Let's state this property again precisely. If f of x1 equals to f of x2, then x1 should equal to x2. Okay. So now coming to the second property, surjectivity. If every element from codomain is being mapped as an output, then we will call that function to be surjective. Our function fails surjectivity because not even a single negative real number is being hit as an output. And the final property is bijectivity. If a function is both injective and surjective, it's called a bijective. And our function is bijective, right? Yeah. So kindly uninstall social media if you said yes to this question. So now let's assess possible queries you might have got. The first one being, if someone just gives an equation like y square is equals to x and questions you if that's a function, be aware that just if the equation is having this convention doesn't necessarily mean that it is a function. You still have the conditions and yes, ask for domain and codomain. Once it's given, you have to verify whether all elements from domain will be paired with exactly one element in the codomain. For this above equation, we shall plot it in Desmos and we can clearly see that for x is equals to 4, we get two outputs which is -2 and +2. This clearly contradicts the condition for a relation to be a function. And that condition was every input should have only one output. So coming to the second query which many students might have. In the example of f of x is equals to x square, since the outputs are never negative numbers, why can't we just restrict the codomain to only set of non-negative real numbers? So this question has a great depth. Firstly, we shall define what range of a function means. Range is the set of all outputs. It's also called as image of a function, okay? So remember that codomain is defined even before we have checked the actual behavior of functions for given domain, and once domain, rule and codomain have been defined, the function is defined. And once we apply the function over the domain, then only we get the range or the image of that function. But if you ask something like, well, now that we know the range, shall we finally restrict the codomain? And would that actually be wrong? Well, that's not wrong though. Both are still valid, meaning that restriction of codomain isn't illegal, but it's just not done for few reasons. Firstly, if you change the codomain, it's not the same function anymore. We knew that, right? So in f of x is equals to x square, defined as f goes from R to R, If you change the codomain, the function itself has changed, irrespective of rule remaining unchanged. We knew that, right? So also the fundamental properties are being affected now. First function wasn't surjective, and once we restricted that codomain, now the resulting function is surjective. Apart from this, there are other reasons and we shall cover them in analysis. Now let's not complicate much here. Mainly just remember that it is usually f defined from R to R. Doesn't mean it's lazy definition though. It also has something to do with the unique properties of real numbers, being continuous, which supports calculus and algebra to function together neatly. Often we choose R to R because it is convenient and standard, especially for calculus. Later, we shall go to more depth of function space and complex numbers, completing algebra. But for now, let's keep it simple. Now, coming to one possible misunderstanding. Remember that a function maps unidirectionally from domain to codomain. I mean, the order of the pair has to be maintained strictly. So, if we have f goes from a to b, there might exist another function g which maps outputs of f from b to inputs of f from a, defined as g goes from b to a. If such function exists, we call that function as inverse of f. And how do we define invertibility of f? A function is invertible if and only if it is bijective. That's it for today. And in next video, we shall cover the concept of instantaneous rate of change. If you have any feedback, feel free to drop it in the comment section and we will definitely consider that. If you found this video helpful, kindly share it to your friends and do subscribe to our YouTube channel. Thank you.